Okay, so we have the next question right here. It says a uniform door of width W is supported by two hinges X and Y. X and Y are vertical distance L apart as shown. State the condition needed for the door to be in equilibrium. Okay, so now this is a very easy question right here. You just need to tell the conditions for a door to be in equilibrium position, right? So there should be no resultant force, right? It should not be moving at all. And the second thing is that there should be no resultant moment, right? The door should not move clockwise or anti-clockwise. Like if you, for example, remove this hinge Y, right? Now the door is not equilibrium and it will move like it will. If you've seen, it will move like, for example, this way, which is clockwise, and it will tilt a little bit like this, right? It will become something like this, and it is not equilibrium anymore, right? So it should not have any resultant moment, right? So you have to say these exact same things, that there should be no resultant moment and no resultant forces, right? So this is your final answer. Okay, so we have the next part right here. It says give the meaning of the term center of gravity. It is very simple. Let me explain you. So this is a box right here, and let's say the mass is basically like distributed across the object. Now, if you want to find where the weight is acting normally, it is considered to act at the middle of the object, right? If it's plane, like at the ground, if it's tilted, then the weight basically position changes, right? So for example, it's tilted a bit like at an angle, right? So then the weight will act like this, it at a very different direction, right? Before it was acting down, now it's a bit tilted, it has some angle now. Okay, so this is what we have to tell, like it is the, we consider a point where the weight might be acting, that is meant by the center of gravity. So the point at which the weight of an object is considered to act. That's it. This is your answer. Okay, so we have this next part right here. It says the diagram shows the force acting on the door at each hinge. The mass of the door is given. The weight of the door causes a moment at about each hinge, and then show the horizontal component of the force of hinge Y on the door is 40 newtons. Length and width is given. Okay, so we need to take any one of these 2 points as moment. So I'm going to take X as moment because we need values from Y. We need the force from Y. So let's see what forces are acting, right? One of is the Y force and other one is the weight, right? So the weight causes an clockwise moment, and this Y, as you can see from the direction, it is causing an anti-clockwise moment, right? So this is weight and this is Y, right? So yeah, now we will move on to the calculations. So to get weight, we will use mg and convert this mass into weight. So it's 14.4 times 9.81, which will give me 141 newtons, right? So the next thing we need to do is tell the examiner that we are taking moment at x, right? And by taking moment at x, we will be using the formula, which is clockwise moment is equals to anti-clockwise moment. Okay, now clockwise moment is our the mass of the door, the weight. So we will use the moment formula, which is Fd is equals to F times t. F is our weight, which is this 141, and distance is the width but divided by 2 because it is now for now acting at the center. acting at the center. So it is 0.85 divided by 2, and you need to find the force for the y. And for the distance, the length is given, which is from x to y, right? It's not the whole door, it's basically from one pivot to another. So it's 1.6, right? And then if you calculate this f, right? So you will get what value? You will get the value as 37.5 newtons, right? If you round it up, it can be 38 newtons. So you just have to prove it. So this is your final answer. Okay, so the next part says that the vertical component of the force of each hinge on the door is equal to the half of the weight of the door. So this is the main point. And hinge Y exerts a force on the door at an angle theta to the vertical as shown. Determine the force F and the angle theta. So as from the previous part, you remember we calculate the force horizontal component, which was 37.5, right? And the weight, which was 141. Yeah, we will use in this part as well. Newtons. Okay, so first, as we have a lot of work to do in this part, we need to draw the vector diagram completely, right? So this is our resultant part right here. And to get into this direction, right? This is the force direction, the resultant force. So in order to get to this direction, you can only use up, down, left, right. So I will go first up and then I will go to the left side. Okay, so this is your vector diagram here, right? A simple version of head to tail rule. And then this is your angle and this is your right angle, right? Oh, let me draw it a little bit bigger so it's much more visible. So it's this is your F, and then you go up and then you go left, and this is your angle, this is your right angle, and your value, which was 37.5, this was your horizontal value, and this is your vertical value, which was the, it says that the half of the weight of the door, the vertical component. So it's 141 divided by 2. So we can calculate either one of those, like force or theta. Let's calculate theta first. So theta, for theta we will use the tan formula. I think the tan formula works because we have opposite and adjacent. So tan is opposite over adjacent, right? The base. So opposite is 37. So wait, tan theta is equals to 37.5 divided by 141 by 2. And you will have to use the inverse of tan, right? Tan inverse, if because the tan goes here. So it's tan inverse by 87.5 divided by 141 by 2, right? And then if you put this in your calculator, your scientific calculator, you will get around value like 228 point theta something, right? So this is the rounded off value. And now we will calculate the force, right? So the for force, we can use the formula of a square plus b square is equals to c square, right? So for this, we have these two are, you can either do one of these, like this is, let's say this is a and this is b. C is always the resultant, but you can switch these up, it doesn't matter. A, B, and C, right? So a square plus b square is basically 37.5 square plus b is 141 by 2 square is equal to c square. Now if you shift this square root over there, it becomes c is equals to 37.5 square plus 141 by 2 square and this square root, and your answer for C will be 80.0 Newton, which is rounded off value. And you can write it here as well, 80 Newtons, okay? So you have force 80 Newtons and you have angle 28.0 degree. So basically this is your final answer. Okay, so the next part says that an identical door is supported by hinges that are much closer together. Explain how a smaller value of L affects the F and theta. You should consider the moment at about point X. Okay, so they have given us the moment about point X. So if we take that moment about X, right, it's all from the previous part, right? So when we took the moment at X, we use clockwise is equals to anti-clockwise, right? Anti-clockwise, okay? So then we have F into D is equals to F into D, and then we made F as subject, so it was F into d by d. D was basically, this was for the weight, where it had weight and some length of the width divided by 2, and this was basically the length from the hinges. Now this length is decreased, right, from the hinges, so the force value will increase, right? This horizontal force value, right? So your horizontal force component value has increased. Okay. Now, if this is increased, then basically now we did the next part where we found its F and theta, right? So the theta we found using the tan theta is equals to the value of basically the force we found, the horizontal component force we found, and the weight, which was divided by 2, if you remember from the previous part, right? And then we did tan inverse and blah blah blah, right? Tan inverse blah blah blah. Okay, so if this increases, then the tan value also increases, the theta value increases, the theta value increases if the F value increases. And now we were left with force, right? The resultant force value, right? So we did that a square plus b square is equal to c square, right? So we were finding this c. And if, let's say, I don't remember what did I consider, but anyways, if you consider even this is greater or this is greater, your c value will be always greater. Okay, so your theta and f values are increasing when your these hinge points are a little bit closer together, right? Your length L is decreasing. Okay, when your L length is smaller, L length is smaller. Okay, so now what we need to do is we have to explain the same thing. It was the clockwise moment, right? Equals to anti-clockwise moment, where we say that mg times w by 2 is equals to f horizontal times L. And basically the, you know, so from this result we got that the horizontal component for f increased, right? The horizontal part component F increased, and then due to which the theta value and the resultant force value also increased. The C part also increased due to it, right? So you just have to explain all of these points, and yeah, just tell them all of the points that we did in the part 1 and part 2, and then it will be your answer, right? So this is your sample answer.